Why don't we move on to speaking of immunology, Dr. Joe Curry, who is professor of otolaryngology at Thomas Jefferson University. He is currently the division chief and vice chair for research in the Department of Otolaryngology. He is a vice chair of the Clinical Research and Population Health Committee for the American Head and Neck Society. And he is going to give us a chat on immunological implications of tissue engineering and biomaterials.
All right. Well, thank you, Dr. Wax, for the introduction. And it's tough to follow such great presentations and research. And it's a real honor to be here with all of you guys who have presented some of the awesome work that you're doing. I will just take it back a little bit and talk a little bit about some of the basics of bioengineering and some of the implications that the immune system has, right? I mean, I think from when we think about transplantation, when we think about implants, so much of what we deal with in terms of the challenges and the struggles have to do with the immune system and its response to the materials that we're putting into the body. So, you know, looking at sort of the origin of biomedical engineering, I was digging through this, and the first reported bioengineered prosthetic was actually Queen Vishbala from India, who in 1500 BC lost her leg in a battle, had an iron leg made so that she could go back out and fight again. So certainly a humbling story, quite tougher than me, at least, I'd say. But the world of biomedical engineering and tissue engineering has expanded so greatly, as you heard a lot about tonight. And so that includes biological sensors, biological materials, biotechnology, nanomaterials, nano implants, and really just a dramatically expanding realm of technology that can be applied to the practice of medicine and to enhance what we are doing. You know, we look at the materials we have, but as I mentioned, we have quite a few challenges associated with that, right? We put in our great a sort of inert titanium implant or our biointegrating dental implants, and sure enough, we often have the complications that we can see with, you know, extrusion of our hardware, necrosis of our bone, exposure of our dural grafts, or other associated problems. At least I know I have these. So what is that sort of process, and what is the most basic process that we deal with when it comes to our immune response to foreign material? And I want to just sort of simplify that to the two key areas, right? When you first place that graft in, there's an initial inflammatory response, and then there's acute inflammation with migration of a lot of different immune cells, particularly neutrophils, and then macrophages play a tremendous role throughout the process of the maturation of that capsule around your implant, be that titanium or breast implant or other implant. And some of the keys in terms of what people are looking at in the future is manipulating that process, moving it away from that acute inflammatory process or that foreign body reaction and the development of a fibrous capsule more towards a chronic, more tolerant immune environment. And that's not that different to what we're doing in cancer as well. We're trying to manipulate cells like macrophages to either become more or less tolerant depending on the response that we want to achieve. Now, that sounds relatively straightforward, but as you can tell, you know, the BMP has many more functions than just bone morphogenesis, right? It has many different signaling pathways that it interacts with and many different targets that can be either beneficial or harmful, which is the fear, of course, in cancer with using growth factors. But that application becomes important when we start to look at biomaterials as well. And so biomaterials can have intrinsic immunogenicity, right? So the materials we put into the body will trigger a response. Through time, people have studied this and have come to understand that we can actually tune a lot of these properties. So be they particulate implants or scaffold-based implants, we can actually manipulate the size, the shape, the charge, the hydrophobicity, and that will all alter the immune response to that graft or that implant. So these things can alter. For example, particles smaller than 50 nanometers can pass through the lymphatics, and they can actually trigger higher responses to the immune system. the shape, whether a molecule or a implant is circular or rectangular when it comes to microscopic particulates, can stimulate more of a response. Macrophages tend to react more to longer particulates than shorter particulates, longer particulates than round particulates. And then the surface charge on the molecule will, on the surface of the implant, will also impact immune responses. The more negatively charged tend to actually trigger more of a response. And then hydrophobicity also can be a tunable property of both particulate and scaffold base. So when we speak about particulates, they can be small microscopic particles, as you see here under enhanced visualization, but you can also engineer complex structures like lipid bilayers or lipid monolayers that can be carriers for drug targets or also stimulating responses themselves. You can also create scaffold-based implants, which is sort of the other big class of implants that you heard a lot about in the crib grafts and the cancellous bone grafts and the artificial grafts used to regenerate bone. And so by manipulating the characteristics of the surface area of the scaffold base or the content of the particle base, we can alter the immune response to that. And so with particle-based engineered implants, what we can see is we can actually create molecules that are small enough to pass through the circulation and through the lymphatics to trigger responses either in the spleen, the bone marrow, the liver, or even in lymph nodes in certain cases. And so one of the things that we're interested in that we've done some work on previously is bioengineering small lipid composites that are ultrasound detectable. So ultrasound contrast agents that actually either have intrinsic properties that stimulate immune response or that can carry molecules to a target area, such as a tumor, when stimulated or ruptured by ultrasound. So we can actually create a small bubble, if you will, that we can rupture with ultrasound to induce a response. And what you can see off to the right is a molecule that we generated, which we call SC61, which we then can inject either intravenously or subcutaneously, that flows through the circulatory system and passes into the lymphatics and will actually pass to the tumor. We can then actually ultrasound that and stimulate an immune response. So this orange staining here is CD45 staining, showing an immune response to the tumor after the molecule and the complex was triggered, rupturing both the small bubble and stimulating a response itself, which is actually what you see here, or I can show you some data where we actually generate this and then load the microbubble with small molecules. We are particularly interested in transport inhibitors for monocarboxylates. So molecules that are involved in the transport of lactate. So we can actually inhibit the transport of lactate and impact the tumor microenvironment. So we can grow a tumor in the mouse, actually ultrasound it. We can then inject the SC61 construct with or without drug and rupture it. We can then, of course, move on to targeting radiotherapy for that to develop a therapeutic model. In vivo, what we see, and in vitro, what we see is actually when we treat these the animals or the cell lines with our drug targets and our microbubble, that we can actually stimulate immune responses, but also we can intrinsically kill tumor cells as well. Here, what I'm actually showing is the effect of the MCT1 inhibitor, AZD3965, and showing the reduction in metabolism, so triggering some apoptosis and triggering some senescence in that the cell lines. So this is done in a human cell line, but we've also done this in syngeneic cell lines so that we can trigger this in an immune competent model in the mice. And so that's sort of some of the background on particulate-based engineering and some of what we can do with particulate-based bioengineered implants. But you can combine this also with scaffold-based, where you implant stem cells, as you saw earlier, but you can implant immune cells and trigger ongoing responses by incorporating other molecular structures into the polymer itself, such as cytokines or chemokines that trigger either chemotaxis or attract immune elements such as dendritic cells to the polymer itself. So scaffold-based implants are probably what we saw a lot about tonight and what you hear about in general, but these are dramatically advancing and improving significantly. So titanium-based implants can now be covered with different chemokines or cytokines that actually trigger improved immune responses. What you can see here is an example of an implant from a recent publication, again, referring to the phenotype of the macrophages that we can alter, can attract them, and then expose them in the implant to the proper cytokine mixture to then trigger a response. What we like to see in some of these cases is an M2 phenotype, which is sometimes called a chronic tolerance phenotype, or a pro-healing phenotype, depending on the scenario. And those types of reactions, if they're manipulated appropriately, can contribute to improved responses. So while we're not really talking about immunotherapy, I do have some experience there. I mentioned that previously, but we can't really talk about the ability of bioengineering to manipulate immune responses without at least mentioning CAR T. This is sort of the biggest advance in bioengineering for immunotherapy that we've seen in the past 10 years, where you essentially create this small biological machine with an altered receptor that is targeted towards your specific tumor and improves your response and your likelihood. As we know, this is making dramatic advances in hematologic malignancy, and people are hard at work trying to find ways to make this more effective for solid tumors like head and neck cancers. Now, there are a number of ways to combine this, as I mentioned, both with the scaffold-based implants and the smaller implants. What you can see here is a recent publication that used cytokine mixtures implanted into the scaffold to attract and promote the development of stem cells. What you can see to the right here is actually a polymer that includes CCL2, a chemokine that helps actually mature the CAR T cells to promote enhanced response. So these types of engineering can be combined together to improve responses and to improve the efficacy. Now, how does this apply to reconstruction? Well, you can see that these types of things, such as bioengineered implants and wound dressings, are on the cusp of development. This one is actually entering clinical trials. So this has biosensors included to detect the temperature, to detect the adherence, and to also administer an electrical signal onto the wound. When you administer a low voltage signal, you can actually stimulate migration of immune cells into the wound to promote wound healing, but you also then kill local bacteria. So it actually has an antibacterial effect as well. And this is a very interesting product, which a number of different people are experimenting with this and similar types of smart dressings, smart bandages. We all use dressings such as Integra, right? So biological dressings that are designed to be a scaffold, but we are on the cusp of seeing the development of scaffolds that include the stem cell application for topical areas such as burns, just like you saw in the earlier talks on reconstruction of the mandible. Impregnating grafts and scaffolds with keratinocytes, fibroblasts, mesenchymal cells, and hair follicle cells have all been researched and demonstrate some benefit when improving wound healing with these types of scaffolds. And finally, I just wanted to mention some of what's being done in nerve grafting. We talked a little bit about this, but there are several key steps in this process, right? So you need topographical cues for the nerve to grow across the graft. We know that only a small fraction of nerve fibers actually grow across a nerve repair. It looks like approximately 20% in some facial nerve studies. We need to improve that substantially to improve the quality. And so by providing topographical cues, as well as conductive cues that stimulate growth, and then finally biochemical cues that help associate the growth of the neuron across with the proper end stage wiring to the motor unit. And so people are actually actively working on this. And again, this highlights this sort of immune response. We know that when there's excessive collagen deposition, that's one of the key interrupters that blocks the growth of nerve fibers across. And again, macrophages seem to be one of the key features in highlighting and stimulating that, as they tend to stimulate ingrowth of fibroblasts, deposition of collagen, and they can, if they are of the improper subtype, worsen the outcomes. And so these are some of the active areas that are being studied in and bioengineering with respect to the immune response. I'm happy to take any questions.
Really fascinating stuff, and it makes you really think about, not the wound care issue is a very interesting one, and the fact that we're harvesting skin grafts in an age when we can kind of generate these cells and create monolayers, and I guess it's a speed issue, like how quickly could you do it, or could you do it before you ever go to the OR? I mean, the science is moving quickly, and you really demonstrated in this talk beautifully that the concepts are limitless, from small molecules all the way to just simple wound care, which is a major cost for the U.S. healthcare economy. How do you use these factors and tissue engineer ways to close stubborn wounds and diabetics, and others. So it just, you have to really digest all the stuff you just put out there, but it is very thought-provoking.
Yeah, the smart dressings in diabetics are absolutely an area of interest. There's quite a bit of publication there. You touched on that very nicely, and it's really a high point that is, from a practical standpoint too, the smart dressings actually can communicate remotely with devices, with the EMR, or with a phone or an iPad. And so that allows you to keep track of real-time biometrics on some of these things. It's amazing what's being done.
Yeah. Yeah. Well, adding, one of our researchers, and you touched on this too, adding electrostimulation or different stimulatory factors, whether it's electrostimulation or otherwise, to these stem cells to help induce migration, growth, differentiation, whatever. It sounds so, science fiction, but it's actually really on the precipice of happening. It sounds like.
Yeah.
Very thought-provoking talk. Really terrific.
Dr. Curry, I had a question for you. I know I've used ACell, which is porcine matrix, and their claim to look at the science is that upregulate M2s versus M1s.
Yep.
Have you looked into that kind of feel for your regenerative immunotherapy?
Yeah, I mean, that's a super common theme, is this sort of M2 versus M1. And if you're sort of a macrophage expert, people kind of get offended. Oh, it's not just M2 or M1. There are many different phenotypes, which is true. But if you look throughout the wound healing literature, M2 is the phenotype that you want to target, right? It's generally sort of a chronic inflammatory phenotype rather than the acute pro-inflammatory M1. In cancer, we would, a lot of times we think we'd rather have an M1, right? That's stimulating an immune response. It's pushing you away from the chronic tolerance or anergy or senescence that we see in the immune response. But in a lot of cases, that also is promoting ingress of tissue destructive immune responses, which is great for cancer, not so great for wound healing. And so there is a lot of work to look at how to sort of stimulate that from a chemokine or paracrine or cytokine standpoint, right? So either trigger the differentiation into M2s from monocytes and sort of tissue resident undifferentiated macrophages. But that's one of the big challenges.
Perfect.
If you look over and over again, it's macrophages that seem to be key.
Yep.
So
I have
what's
a
your,
question.
yeah, sorry,
I'm sorry, go ahead.
what's your area, Joe, of research that you're really focused on here?
So right now I'm mostly interested in sort of generating these new lipid monolayer molecules, right? So we've engineered a few that actually trigger a nice immune response and augment immunotherapy. And then we're also loading them, because it's like essentially a small lipid sphere. You can load that with small molecules. So we can load that with metabolic modulators, which is what I'm kind of interested in most cases. And so looking into migrating some of that cancer work into reconstruction is something new that we're sort of kicking around in terms of ideas, because we've done some work and we've actually shown that we can increase M2 macrophages, and that's part of what we're interested in.
So, very proactive and very thoughtful lecture. I mean, very amazing work that you're doing. One thing that you touched upon was cancer and growth factors. And immunotherapy. So, what are your thoughts about using growth factors in patients with cancer or potential cancer?
I mean, I think it's a good challenge. I mean, you know, the real question is sort of the medical legal, right? Right. I mean, that's what we fear,
Yeah.
right? I mean, because
Yeah.
the challenge, but in reality, does BMP trigger a possible response or stimulate disease if you've completely resected it? I mean, I think it's a scientific question that needs further exploration, right? Most of the time when we think about, for example, okay, anti-PD-1 is a major home run, right? It works, right? But think about all the other add-ons that people have tried. People have tried to use IL-2 and anti-IL-2. And the problem is these molecules have very complex interactions, and some of them are pro-tumorigenic, some of them are anti-tumorigenic. And so I think the answer is probably very specific to the individual cytokine or chemokine that you would use. And then also probably less scary than we think it is, but I think you would have to do a lot of hard work to prove it.
What's interesting is both me and Arshad in Miami and Bob Marks would throw BMP in patients who were far less than 5 years out. And really, from a standpoint, I think I was there for 7 years, and his recurrence rate was no less or more than anyone else. So from my standpoint, I don't think BMP and PRP use a lot of that, and bone marrow aspirate. If it was true, I mean, it was I guess it's another stimulant for a cancer recurrence. He would have a bunch of lawsuits, right, and a lot of dead patients.
Yeah.
But reality is, he treated a lot of cancer patients, ORN patients, and his numbers are no better or worse than anyone else regarding recurrence.
Yeah, I think if the tumor's out, right? But
yeah, the fear is awakening sleeper cells and
minimal residual disease.
Yeah.
But I mean, I think if you clear it, and how long is that BMP going to stay around? I mean, there's so many unanswered questions.
Yeah, 21 days. And it's
really
funny,
study
and he would
really study it.
He would do that argument, and it perfectly makes sense. And then there was some drawback, I guess, regarding the nerve. A lot of it's weird. It's people. Their arguments are kind of, when you look at it, is that you don't want to do an allograft for regarding nerve because there's a potential for recurrence. I was like, it's just a scaffolding. That makes no sense. Absolutely 100% makes no sense. But that's our argument for not doing allografts when in a cancer field. So.
Well, what a fascinating, panel, and what a fascinating discussion on so many different aspects of reconstruction and so much really cutting edge science that I think is just going to drive the field. And I remember one of my early fellows, their primary goal was to be able to use cytokinetic factors to drive stem cells to form bone, soft tissue, and maybe they would do some soft tissue free flaps for revascularization, but it would get rid of all the bone reconstruction. It would get rid of a lot of the morbidities that we see now, and sounds like we're getting closer and closer to that. And that whole thing, Joe, that you presented with like a Band-Aid. I mean, this is like science fiction. Just sounds straight like out of science fiction. And maybe, combining that with Eric, your work in getting, your not transplants, but the other grafts and growing them. It's just fascinating where we're going. So it really invigorates me to think, no, another free flap. We're never going to get beyond this. There's nothing more to do. It's really invigorating to hear this and to hear all of this stuff.